So far we've learned about kinetic energy, and we have a formula for it. Kinetic energy is 1/2 mass times speed squared. An object that has kinetic energy is capable of doing work. For instance, if you swing a hammer, that hammer has kinetic energy and it can hit a nail. It can apply a force over a distance to the nail. Now, we just introduced this idea of potential energy in the last lesson. Objects with potential energy can also do work. For instance, if you hold a brick high in the air, this brick has gravitational potential energy. If you let it go and drop it, it falls to the ground, and it can do work by striking an object on the ground. Now, potential energy is the property of a system, not just a single object, but it actually requires two objects. So it depends on the relative position of those two objects. In the case of gravitational potential energy, it depends on the relative position of the two gravitating objects, which in most cases is going to be planet Earth as one object and whatever the other object is, like the brick. So the distance between the brick and the Earth is the important parameter. Each type of conservative force has its own mathematical formula for its potential energy function. And in all cases, the work done by a conservative force is minus the change in potential energy. The work done by a conservative force is the negative of its change in potential energy. Now, the first type of force that we'll define a potential energy function for is the gravity force. It has a really simple expression. The potential energy function for gravity, we'll write PEG equals the mass of the object of interest times G times the height of the objects above the ground. But keep in mind that this height above the ground really refers to the distance between the two important objects in the problem, which are the mass and the Earth itself. Later on, when we talk about Newton's law of universal gravitation, we'll have a more general function for potential energy. This is kind of the simplified one that goes along with our simplified gravitational force, mg. So with these concepts in mind, we can now write down kind of a full expression for the work-energy theorem. Remember, the work-energy theorem says the net work on an object equals its change in kinetic energy. Now, this net work, if there are several forces acting on an object, could be due to a non-conservative force and a conservative force. And for the time being, since the only conservative force we've learned about so far is gravity, let me just focus on gravity here. Later on, we'll expand this to include all types of conservative forces. But we can replace this work done by our conservative gravity force with minus the change in potential energy and one step of algebra gives us a more complete version of the work-energy theorem. It says that the work done by any non-conservative force on an object equals that object's change in potential energy plus its change in kinetic energy. Now, one note about this gravitational potential energy function. We need to define a 0 point for y, where we're measuring the height from. It turns out that that 0 point is totally arbitrary. If you want to pick it at ground level, that's fine. If you want to pick it at some other height, that's totally fine. The reason why this is arbitrary is because whenever we deal with potential energy, we're really dealing with a change in potential energy. So that change will show up as kind of a delta y. So it doesn't really matter where 0 is, only matters how far you've moved.